Hey everyone, I'm just letting people arrive and then we'll start in just a minute.
Okay.
How's everybody doing today?
Doing pretty well.
Good.
Yeah.
You guys were asking me about 4.2 and whether that's going to be included on the quiz today. I think let's do this. We're going to have to finish up 3.9. So we've got the whole continuous random variable discussion to have. And then 4.2 isn't very long as a chapter, and it's kind of interesting. There's some neat stuff in there. Let's see how things go. Okay. If we decide we're not going to include it on the quiz, which I'm okay with if that's what we decide, I still want to try to get through it as much as possible, because next class week is a short week because we don't have class on Monday, right? It's a holiday. And then we also have an exam next Thursday. Remember, we've got like 3 exams. So next Thursday is an exam. So I want to, make sure that we have enough time to go through things and then still be able to do a review. So let's see how things go. I'd like to at least get through 4.2, even if we don't include it today on the quiz. Okay.
Okay.
So just as a wrap up too, we've got quiz this afternoon, right? It'll open up at 4 o'clock this afternoon, and then your homework is due tonight, which if we're not going to include 4.2 on the quiz, then the homework won't necessarily be included, but it'll be due next week. But we'll decide that at the end of class today. Okay, we'll see how far we get on things. Okay. All right. So I'm going to pick up on chapter 3.9 where we left off yesterday. So I've got my 3.9 notes, which at the end of class today we'll have completed them. So I'll scan them in and post them. 3.9 today we're going to talk about continuous random variables and expected values and variance, and then we're going to talk about covariance too. So here we go. Okay, good. Okay, all right. So let's go ahead and continue with oops, chapter. Good, that one's not going to work. Chapter 3.9 continued. Okay, so today we're going to talk about continuous random variables. Yesterday we focused on discrete random variables. Remember, the nature of this chapter is we're talking about more properties of mean and variance. So we're focusing on things like expected value, and then we're also going to talk about covariance, but we'll do that in a little bit. So let's go on to here. So continuous random variables. So we've got X and Y, and these are both continuous random variables. And they have a joint probability distribution function, probability density function. EDF. We'll call that f of xy, xy. Okay, so let's talk about their expected values and their variance. Okay, so first with the expected value, this is like what we did yesterday with the discrete, but now we're going to move into continuous. So the expected value, remember, is our mean, okay, for our distribution. So we're going to call this function g of xy, okay, and this is a continuous function because our underlying probability density function is continuous and our random variables are continuous. Okay, so if we say the expected value of this function, okay, whatever that is, we're going to integrate. I'm just going to write this in shorthand. Okay, so this is double integral here, and I'm going from minus infinity to positive infinity on both integrals. So the expected value of our function is g of xy times our joint distribution, dy dx, or dx dy, depending on how you're going to do it. And this will be, we'll say that the expected value, we can get an expected value if this integral exists. We have to leave it open for it not existing, right? Because if we have an improper integral here, maybe it won't exist. Okay, so, all right. So now we're going to say if our function g of xy is equal to x times y, then just as an example, our expected value of xy is equal to our double integral. So this is across x, summing across x, summing across y. This is like what we did with our discrete, only now we're in continuous. So this is xy. So all I'm doing is I'm defining what that function is, and I'm plugging it into my expected value calculation. dy dx. Okay, so this is the function. I'm going to multiply it by my probability density function, and I'm going to integrate across all of x and all of y. Okay, so if x and y are independent, okay, my expected value of xy is going to equal to the expected value of x times the expected value of y. Okay. Okay, when you guys are ready, I'm going to take out the example 2. So this is my notes, right, for chapter, the lecture note examples for chapter 3.9. Example 2 is what we're going to be looking at and working through. Give you guys a chance to finish writing that down, and then we'll work through the example. Okay. All right,
What's
so
the top of the notes?
I'm sorry, the very top. Very top was just a definition. So we have continuous random variables, right? It's just defining that we have x and y are the two random variables that we're working with within our joint probability density function. And both x and y are continuous random variables within this structure, the PDF.
Okay, thank
Great. Okay. All right. So let's talk about example 2 from 3.9. All right. So x and y are two continuous random variables. Okay. And they've got a joint probability density function, f of xy equals 4 times x times y. And x goes from 0 to 1. And y goes, this looks like an O, y goes from 0 to 1. Okay. Now we've got a bunch of things that we want to ask. We want to find out, is this PDF a valid PDF? Okay. What's the probability that y is less than x? What are the marginal density functions, the individual density functions? What are the expected values? This is just a random letter. What are the expected values for e of x and e of y? Are they independent? And what are the variance of x and the variance of y? So there's a whole kind of, this is a really great example. There's kind of gives us all this great big picture of what's going on. Okay. So you don't have to draw anything out when you're doing these things, but let's just take a look. I want to show you like what these things look like in terms of graphing to think about. I hope you guys have had a chance to take a look at that 3D surface plotter. That'll help a lot. So this is one. This is one. So because x and y are both between 0 to 1, so this is 0. So you can kind of think about our base as being this right here, okay, because x and y both go from 0 to 1. Now, z equals 4xy. So that's like saying, I think it goes something like this. And it's going to look like, and this is our structure here. So it's, you know, kind of this planar object. Okay, so this is our joint probability density function between x and y. Okay, it's a volume, right? So our probability, okay, is within here. All right, so just to kind of give you, you guys don't have to plot these things out, but I just want to give you a chance to kind of think about what it means to have two variables in our probability. It's a 3D structure. We often plot it with just the x, y, and that's really just this base plate, right, that forms the base of this three-dimensional structure. Okay, all right. So part A is our joint probability distribution function of valid PDF. Okay, so how do we know if something's valid? Because when I sum it up across the boundaries for both x and y, the probability should sum to 1. Okay, and also all the values within it should be positive, should be non-negative. So let's take a look. So is f of xy must be non-negative. And we can see that, right? So if x goes from, oops, sorry, you can see that. If x goes from 0 to 1 and y goes from 0 to 1 on this function here, our probability density function is always going to be positive. Okay, so that's true. Okay, the next part is that our volume of our solid, which is the integral across this whole area, must be equal to 1, which is another way of saying that all probabilities sum to 1. Okay, so let's go ahead and do that. So I've got my margins for x and y. Right, my bounds of integration go from 0 to 1 for x, y, and it doesn't matter if I go dx, dy, or dy, dx in this case. I think I just happened to do dx, dy. So now I'm going to integrate. When I do this, right, the 4y passes through and the x gets processed with the power rule. So 0, 1, so I'm going to get 4y x squared over 2, and I'm going to evaluate that from 0 to 1. And then I need to integrate with respect to y. Okay, so this is going to look like 0 to 1, 2y dy, which is equal to y squared from 0 to 1. Okay, and then when we process this with our fundamental theorem of calculus, we find 1 squared minus 0 squared is equal to 1. So that's good. So yes, it's a valid probability density function. All probabilities sum to 1. Okay. All right, our next question, part B, says, what is the probability that y is less than x? Okay, so what does that mean exactly? I'm just going to visually graph it out just a little bit. Right, so I'm just going to plot the base plate here. So in terms of my x and my y axis. So before we said that x and y went out to 0 to 1, right? But now in this case, y is going to be less than x. So here's our line. This is our line y equals x. Okay, so all values where y is less than x fall in this shaded region right here. Okay, right across this line. So that's like saying this line right here. Oops, sorry, you can't see what I'm doing. This line right here, right, where y is going to be less than x. Okay, I'm kind of cutting that in half. I'm looking for that part of the probability of my whole structure here. Okay, but just in terms of thinking about our base plate, this is what we're doing here. All right, so I'm going to take my joint PDF and I'm going to work on my integrals. Okay, so what this means is, right, we're going to think, let me write it down, then we'll talk about it for xy, dy, dx. So in this case, right, our y is going to be less than x. So I'm going to integrate with respect to y first, and y is going to go from 0 to x. Okay, so wherever, like, I'm going to go from 0 to x. 0 to x, 0 to x, 0 to x, all of these different possibilities. So those are my values for y. Y goes from 0 to x, and my x goes from 0 to 1. Okay, so that's how we're thinking about what this means. So when I integrate with respect to y, going from 0 to x, I'm going to get 0 to 1, 4x y squared over 2, evaluated from y equals 0 to y equals x, and then dx, which is going to look like 0 to 1, 2x times, this is x squared minus 0 squared, just so you can see, and then dx, okay, which is going to be equal to 0 to 1, 2x cubed dx, right? 2x times x squared gives me 2x cubed dx, and I can just do power rule on that, which is going to give me 2 over 4 x to the 4, evaluated from 0 to 1, which gives me 1/2. Okay. So the probability that y is less than x is equal to 1/2.
I'm so sorry. Could you explain again why you can go from 0 to x, but then 0 to 1 for y, and why don't you go 0 to y also, or 0 to 1 for both?
Right. So 0 to 1 for both is going to give us a number, right? So 0 to 1 for both is what we did in the first part, where we're looking at the area of our whole structure, right? So in the very first part, 0 to 1 was our bounds for x and y. Oops. Oh, let's see, our bounds for x and y, right? And so in the first part, in part A, I'm looking for the volume. So if I integrate 0 to 1 on both of these integrals, I'm going to get a number out there, which tells me when I do this, right, the total volume, okay, because that's like saying on here, you know, y is going to go from 0 to 1, x is going to go from 0 to 1, and what we're doing is we're basically slicing up all of these little slices as we go, and we're counting them up or summing them up. And so we're going to get the volume equal to 1. Okay, that was the first part. On the second part here, we're setting this bounds here. We're like, you know, before when we said what's the probability that y is less than 1/2, or what's the probability that x is between 0 and 0.25. Okay, so that would give us the bounds for our integration when we're looking for probabilities. Okay, so when you're asked for what's the probability, you're thinking about your bounds of integration. Okay, so when I do this, what's the probability that y is less than x? That's like saying I'm going to redefine this so that y starts at 0, and now it's going to go to x, right? So that's, I'm asking what's the probability that y is between 0 and x, is how you can also think about this, right? When I set this up right there, I'm redefining what my boundaries are. So this sets up a dependency, right? It's not like a number. Like if it was an actual number where you said, what's the probability that y is less than 1/3, then I would integrate from 0 to 1/3 and then 0 to 1 on my x. Okay, that would give me an actual number. Okay, and here I'm still getting an actual number, but now y has a dependency because it's dependent on what's the value for x. Okay, but it's based on how we've defined the question. We're asking a variable question, right? We didn't say very specifically y is less than some value. We want to know y is less than whatever x is. Does that answer your question a little bit more?
Yes, thank you so much. That
Okay.
makes a lot more sense.
Good. It's going to depend on like what you're being asked to do too. So keep that in mind. There's no like hard and fast rule. You have to read the question and kind of think about what's happening. Okay. All right. So probability y is less than x. All right. So now part C says, what are our marginal probability density functions? All right. So let's take a look. So part C, marginal PDFs. Okay, so we're going to basically take our joint PDF and we're going to pull it apart into the X PDF and the Y PDF. Okay, so I need to think about it. So let's just write down what we have. So X is between 0 and 1, Y is between 0 and, so they're not like dependent on each other per se within the definition of our joint PDF. And then our joint PDF, I'm just rewriting it here for X, Y. Okay, so that's going to help me think about it. So now remember, just like we did with the discrete, but now we're doing it with our continuous. So to get my marginal PDF for X, I have to sum across all of my X values, X, Y, but with respect to Y. So across like whatever my X values happen to be, I have to sum across all the Y values in order to get that. So when I do this, I'm going to get 4x y squared over 2, and this is going to be y equals 0 to y equals 1. Okay, I'm writing this in because we've got two variables so that you know which one we're plugging in. This is going to give me 2x, and that'll be true when x is between 0 and 1. Okay, so we'll do the next one. Now, why didn't I evaluate this from 0 to y or 0 to x or whatever? It's because, right, the definitions for how my variables were defined were set up between 0 and 1 and 0 and 1. I guess we'll do the same thing for our y. Okay, so I'm going to integrate from 0 to 1, 4 x, y, and I'm going to integrate with respect to x, right, across all of my y values, but I'm doing it for all the different x values that are possible. It's a little bit easier to see when we do it on the discrete case because we're looking at a table and we can see what these values are, but in the continuous, we're doing the same thing, but it's continuous, right, which is why we're using the integral. All right, so now this is with the x. I'm going to get 4y x squared over 2. Oops, sorry. This is x equals 0 to x equals 1, okay, which is going to give us 2y is going to be valid between y equals 0 and 1. Y is between 0 and 1, okay. So these are our marginals. So I can put this together to make it just look a little nicer. So f of x, oops, x equals 2x, and then fy, y equals 2y. To summarize. Okay, so now I've got my marginal PDFs from my joint PDF.
So if y was from 0 to 2 though, you would have plugged in y equals 0 and y equals 2 for f of x, right?
This is summing across, wait, for this one, yeah, so we're summing, yeah. So if this, for example, if our y bounds were from 0 to 2, and I'm summing, calculating my f of x, right? And I'm summing across all y, this is, let's write this in, this is y equals 0 to y equals 1, x equals 0 to x equals 1. And we went from 0 to 1 because those are the bounds that were defined for our joint function, right? Those are the bounds that made all the x values went from 0 to 1, all the y values went from 0 to 1. For example, like you said, if y goes from 0 to 2 instead, then I would have had 0 to 2 right here in that first integral because I'm summing across y. Does that make sense?
Yes, thank you.
Okay, all right. There's a lot of details, a lot of little details floating around that we have to take into account here. All right. Part D, we want to take a look at our expected values. So we want to go E of X and E of Y. I want to think about what those are. Okay, so let's think about it. So we've got our, let's write down our joint f of x, y, and we've got our bounds. Okay. Now to calculate E of X, 0 to 1, okay, I'm going to go 0 to 1. I'm going to go X for XY, dx, dy, okay. From here, I'm going to calculate out 0 to 1 for x squared y, dx, dy, which when I do the power rule, sorry, I forgot one of my integrals, 0 to 1. I'm going to do the x part first, right? Because that's how I've said I'm going to integrate the x ones first, which means I'm going to get from 0 to 1, 4/3 x cubed y. This is from x equals 0 to x equals 1. And then we have to integrate our y after that. So then this is going to be 0 to 1, 4/3 y dy. And with the power rule, whoops, sorry, I've already done it, 4y squared over 6 from 0 to 1, which is going to give us 2/3 is our expected value for x. Okay, we took our joint PDF and we did x times E of xy. Okay, we integrated across the whole thing because I need the whole volume, right? So I need to take a look at the whole volume, and I said, what's the expected value for x? That's why I'm multiplying by an x there. We're going to do the same thing for y. I'll scroll that up so you can see. Okay, so E, y. We're going to go y for xy, dx, dy. It doesn't matter in this case if you want to do dx first or dy. It's not going to change the complexity of it or change the answer. 0 to 1, 0 to 1. So this is going to be 4xy squared, dx, dy. That's a 2, 4xy squared. Okay, which is going to be 0 to 1, 4x squared over 2y squared. This is x equals 0 to x equals 1. And then we're going to integrate with respect to y. 0 to 1, this will be 2y squared dy that we get when we integrate with just the power rule. Okay, we're going to get, oops, sorry, 2/3 y cubed from y equals 0 to y equals 1. You don't have to write in y equals 0, y equals 1. I'm just putting that for you to see like which variable it is that we're working with, especially here, okay, so you don't get confused when we're working on it. So that's 2/3, which is our expected value for y. Okay. Give you guys a chance to finish thinking about it. Can't tell if you're still writing. I'm going to start to change the page. Is everybody, is anybody still writing? You want me to wait? Okay, great. Okay, so part E says, are they independent? Okay. Okay, so we're going to use our expected value to help us answer that question, right? So if they're independent, right, remember, I can take a look at my joint distribution, probability density function, should be equal to the product of the marginals. Okay, I can also use my expected value too. So we're going to say 4xy is equal to 2x times 2y, okay, which is actually equal to 4xy. Okay, so now we can
Is this how
conclude.
you would prove it for discrete?
We do prove it for discrete. Yep. Well, you mean like, but we're doing continuous. Are you? You're talking.
Yeah, I was just asking like in it like a side note basically.
Oh, side. Yeah. So it's the same thing, right? So we're using our individuals, okay, to multiply together to see if we're going to get back our joint, right?
Okay.
Yes. It looked promising when we saw the definition for our joint distribution where x was defined with its own bounds from 0 to 1 and y was defined with its own bounds from 0 to 1. It looked promising. It wasn't a guarantee that they were going to be independent, but definitely if they have been defined with their bounds being like 0 was less than x, which was less than y, which was less than 1, already there's a dependency that's built into that. Okay, so you still have to prove it, right? And the fact that the bounds are defined separately doesn't guarantee they're going to be independent, but it's more promising. Okay, now part F says, what are the variances? And we want to find out what our variances are for these variables, random variables. All right, so let's see. I'm going to say sigma x squared equals our variance. This is our variance of x, which is going to equal to e of x squared minus u of x quantity squared. This is our shortcut method, right? Okay, shortcut method I like. There's less algebra involved, less chance for me to make a mistake. I still do have to calculate out this part though. So I'll go ahead and do that now. E of x squared. So I go from 0 to 1, 0 to 1. I multiply x squared times my joint distribution. Okay, which is going to look like 4x cubed y dx dy, which is going to look like x to the 4th, 0 to 1.
Could you move
y.
the screen up a little bit?
I'm sorry?
Could you move the screen up a little bit?
Move
Like
this,
a-
move it like this?
yeah,
You're looking at the independent stuff still, huh?
yeah,
Okay. How's that?
that's good.
Okay, so this one's going to be 0 to 1 y dy, which is 1/2 y squared from 0 to 1, which is just 1/2. So that's our e of x squared, which I need here, okay, is equal to 1/2. All right, so that means, can I scroll up?
Yep.
All right, so that means I can say my variance for x is going to equal to, remember, our e of x squared minus mu of x, our expected value, quantity squared. So that's going to be 1/2 that comes from here that we just calculated minus 2/3 is our expected value that we just calculated. So this is our expected value of x, quantity squared. Okay, so minus 2/3 squared. Don't forget to square it, right? Because your variance is always going to be positive. If you get a negative variance, it means maybe you calculated some of these numbers wrong, or maybe you forgot to square it. Okay, that happens. So this is 1/2 minus 4/9, which is equal to 1/18, which is our variance for x. Okay. We're going to go through and do the same thing for y. It's going to look just like this. Okay. Scroll up just a little bit like that. Okay, so I'll start doing sigma y squared. So this is our variance for y, which is going to be the expected value of y squared minus u of y quantity squared. This is our expected value of y. Okay. All right, so let's go ahead and calculate out this bit. So e of y squared is going to look very similar. E of y squared, so double integral, 0, 1. Y squared, now we're multiplying by our joint distribution, dx dy, 0, 1, 0, 1. So this is 4xy cubed dx dy, which is going to be 2x squared from 0 to 1. Oops, sorry. And then y cubed. I wrote that in the wrong spot. No, I was right. Y cubed dy. Okay. And then 0 to 1, 2y cubed 2y 4th over 4 from 0 to 1. And that's going to give us 1/2 as our expected value of y squared. I need that to calculate the variance. Okay. All that meant was I'm multiplying y squared times my joint distribution and integrating. And we get the same thing as we did before for the x, which is 1/2, which means you guys can imagine since the mean was the same for the x, we're going to get the same value for the sigma squared, but let's just go ahead and do it again. I'm going to scroll up a little bit. Okay, so now I'm going to say my variance, that's y squared equals, right, this is e of y squared, so that's 1/2 minus my mu of x squared, 2/3 quantity squared, 1/2 minus 4/9 plus 1/18, which is our variance for y. Okay. You guys can see both. Give you guys a second to finish writing all that down. And then we'll talk about covariance. Anybody still need time to write for the example? I'll scan this in and then post it later. Right. Now, we need to ask ourselves, what happens if x and y are not independent? We're going to handle variance then. What are we going to do? How are we going to handle the variance? So then the variance is going to become what we call a covariance. Okay, so like if x and y are independent, then they're both going to vary independently, right? If x and y are dependent on each other in some way, okay, however we defined it so that they're dependent on each other, when one varies, the other one varies, okay, in a specific way. Okay, so there's a covariance between those two. I can't just say one's going to vary and one's going to remain the same because they're not independent anymore. So we need to be able to think about covariance. So covariance we call COV, and we call that x and y because I need two parameters or at least multiple parameters to talk about covariance. So this is going to be sigma of xy, should be sigma squared of xy. This is like saying, actually we call it, right. So this is x minus mu of x times y minus mu of y. Okay. I'll put the squared back in because it's a variance. Okay. Which is really like we can say this is e of x y minus e of x times e of y. Okay. This is our shortcut. This is our long method. This is our shortcut method. Okay, so both I have to take a look at. Remember our variances. Okay, what's happening? What's the distance between our mean and a particular value of x of our variable that we're looking at? Okay, what's our expected value given that distance? Now remember these are our shortcuts. Okay, for how to do that. So that's a good shortcut method. So with the discrete random variable, okay, our covariance looks like I'm going to sum across the x and sum across the y. Okay, this is shortcut here. I'm going to say x minus mu of x, y minus mu of y, times our probability, our joint probability mass function. Okay. I have a continuous random variable. then our covariance for X and Y is going to be, I'm going to sum across the Y's, I'm going to sum across the X's, or the X's and then the Y's, it doesn't matter. X minus mu of X, Y minus mu of Y, times our joint distribution function. Okay, and then dx, dy, ran out of space. Okay, same thing, right? I'm summing, but in continuous, and I'm summing in discrete. Okay. I'm also going to define something too. If A and B are constants, then I can say the variance of AX plus BY. I think you've got some homework problems like this. AX plus BY is going to look like A squared variance of X plus B squared variance of Y plus 2AB covariance of X, Y. Okay. When you guys are ready, we're going to work through a couple examples, one discrete and one continuous. This will be example 3 on your example page. Give you guys a second to finish writing that down.
I have a question.
Yeah.
For when you define covariance, right at the top, when you say expected value XY, how are we interpreting that? Because like I don't know, the only way I've seen expected value is independent.
So expected value is it's like all that means when you do the expected value is I'm taking each X value or each Y value and I'm weighting it by its probability. So if I go expected value of X, I'm going to go X times the probability joint distribution and then sum across both X and Y. When I do Y, I'm going to multiply Y times the probability function and then sum across both X and Y. If I do X, Y, that's going to be X times Y times my probability distribution function, and I'm going to sum across both X and Y. So all this means is when I go to do the calculation E of XY, I'm going to just multiply X times Y times my probability distribution function. We'll see. We're going to do some examples so that you can see how we would calculate E of XY. But all it means is it's the same calculation that we've been doing, same process where we take whatever's inside this argument here and we multiply it by our probability mass or density function, and then we sum across all the X's and all the Y's. That gives us our expected value for X, Y. Okay, let's go through a couple examples. Go ahead.
So okay.
Yeah, we'll go through a couple examples, and I think it'll be more clear when you start to see it worked out. But it's the same algorithm essentially for how we calculate expected value. Okay, so example 3 says, let's see, X and Y are both discrete random variables, and they have this joint distribution function. Okay, we want to find out what's the mean of X, mean of Y, sigma X, sigma Y, and we want to find out what's the covariance of X and Y. We want to calculate it using both methods. Okay, the long method where we subtract out X from its mean and Y from its mean, and then multiply things, and then doing the shortcut method, just so you can see that we actually do get the same values. So
I have a question. Sorry.
Go back to here. Or?
No. I just have a question.
Okay.
So you're saying when we're calculating covariance, the variables have to be independent?
No. This is when we calculate if the variables are independent, then essentially let's see, the parts of it.
Sorry, I meant like not independent.
Yeah, they're not independent. If you go to calculate covariance on two variables that are independent, the covariant part is 0. It'll knock off. Like this part here becomes 0, and so it'll knock off when you're actually working it through. It'll kind of fall out, you know, in the equation. It's just more work, right? There's no need to calculate a covariance when two variables are independent of each other. We do this when the two variables are not independent because they're varying together. They're co-varying, right? Instead of varying independently.
So do we have to prove that they are not independent before each problem if we're asked for covariance?
That's a great question. So, so sometimes we'll tell you that the data are independent, so then you know you don't have to calculate the covariance. Or we'll tell you that we want you just to calculate the covariance. So that means it's kind of a clue that we're already telling you that things are not independent of each other. But yes, so in real life, like right now, as you're learning it, we're going to tell you this is independent, that's not independent. So calculate the variance or calculate the covariance. In real life, you're not going to know. You're going to have to do the test to see are they independent or not. If they're independent, then you calculate the variances on their own. If they're dependent on each other, like they fail the independence test, then you'll need to calculate the covariance on those two. Okay, so ultimately, as you move along where you're actually using these tools, you yourself will have to test whether or not the variables are independent. While you're learning it in this class, often will tell you, that this is independent or not. Okay. Very good.
Yeah.
All right. Okay, so let's go on to example 3. So I'm going to find the mean and we're going to find the covariance. Okay, so while we're here, I left the space on our table for coming up with the marginal probability mass functions. Let's go ahead and calculate them while we're here. So 1/4 plus 1/4 is 1/2. 1/4 plus 1/4 is 1/2, right? This is going to sum to 1. Let's do it here. So this is 1/4. This is 1/2. This is 1/4. Okay, and when I sum these up, these things are going to equal to 1 on both sides. So this right here, right, is our probability density mass function for y. This right here is our probability density function for x. Okay, just we weren't asked for it, but it's just something while we're here, we're just going to gather the data. Let's see, I think let's see, I asked you what's sigma x, what are they? And I think in this example, I'm going to tell you what mu of x and mu of y are, just to save us some time, because that was how in my equation, my function, I actually had it already defined, so I didn't have to spend all the time. So we could actually calculate the covariance. So our mu of x is 3/2, our mu of y equals 2. And we could do this by calculating out our expected values, but we're just going to jump. I'm going to tell you what these are so we can get right to the covariance part. So our sigma x is equal to 1/2. And our sigma y is equal to radical 1/2. Okay, I'm giving those to you so that we can use them, because I actually want to spend time just talking about the covariance part. Okay, so part C, our covariance.
Do you mean radical 1/2 for sigma y?
Do I mean that? Let's see. I think it may be. This may be also radical 1/2. Let me go back and check. Let me go back and check.
No, I'm saying because you have two.
I know but yeah, I think this is maybe 1/2, and that's just simply radical 1/2 because our means are going to be different, right? Because this one has a different distribution. They're not the two distribution functions are different, so their expected values are different, which means that this is actually like standard deviation, right? That these could be different. I'm going to leave it as 1/2. I can go back and check, but I'm pretty sure it's just 1/2. Okay. I know we're tempted to think it's going to be radical 1/2, but because the means are different, it's possible that the variances are too. But I'll go back and calculate it and check it out. I did it some time ago, so I don't have my notes anymore on how I calculated that. But give me a minute and we'll do that later. All right, so covariance. So now for x and y. So for covariance, let's just write down our covariance. Covariance x and y. This is going to be, I'm going to sum, this is discrete. I'm going to sum across all x. I'm going to sum across all y. This is going to be x minus mu of x, y minus mu of y, times our joint distribution, x and y, okay? And we also have the shortcut. So method 1, we'll do method 1 like this, and method 2 will be our shortcut method. Okay, so let's sum this up. So my particular x value is 1, minus my mean, which is 3/2, okay, times my y value is 1, minus the mean for y is equal to 2, right? So this is, I'm here on 1, 1. So x is equal to 1, y is equal to 1, okay? The mean for x and the mean for y. And now I need to put in the probability, the joint probability for those x and y values. Again, when x is equal to 1, okay, and then y is equal to 2, and then the probability of that happening, plus x is equal to 1, right? Y is equal to 3, and then the probability of that happening. Like you normally wouldn't have to write the 0 part in, but I'm putting it in so you can see that we're summing up all of these different pieces here. Plus now when x is equal to 2 minus the mean, when y equals 1 minus its mean, times the probability for that. X is equal to 2, y is equal to 2, times the probability of that happening. And then the last bit, x is equal to 2, y is equal to 3, times the probability. Okay. This is method 1, where we actually sum up the differences between that particular x value and the mean. Okay, we multiply it by the probability of that happening. Summing up everything, we're going to get that's equal to the covariance is equal to 1/4. We'll do method 2, which is slightly has slightly less algebra. Okay, so method 2 says our covariance for xy is equal to the expected value of xy minus the mean of x times the mean of y. Okay. So my expected, first I have to calculate this bit. So my expected value of xy is going to equal to the sum across all the x and across all the y. That's a y. Sum across all the y. I'm going to go xy times my probability mass function. Okay. So we're going to plug things in here. So when I sum across everything, I'm going to go x is equal to 1, y is equal to 1, times the probability of that happening, which is 1/4. I'm looking at the table. Plus x is equal to 1, y is equal to 2, times the probability of that happening. Plus x is equal to 1, y is equal to 3, the probability of that happening. X is equal to 2, y is equal to 1, times the probability. Plus x is equal to 2, y is equal to 2, times the probability. X is equal to 2, y is equal to 3, times the probability. Okay, I just rolled through the table here. These values and these values here. Okay, summing up across. This is just for my first part of my covariance calculation. When I do this, I got 13/4. That's just for this e of xy. Okay, so now I need to plug that into here. So my covariance xy is going to be equal to e of xy, so 13/4 minus 3/2 times 2. Okay, which in the end is going to equal to 1/4. They should be equal to each other. They're just two different methods. Okay, personally I like this one better. I have less chance of making a mistake. Usually the math is a little more simple, but it's up to you. You have two methods to choose from. If you're asked to find the covariance of things, you can do whichever one you want. Use whichever method you want. Okay. So that's for the discrete case. And then we'll, when you're done writing this down, we'll move on to a continuous random variable. Okay. Everybody else set? Anybody still writing?
Hold on one sec.
I will scan these in later too if you need to check to make sure that you wrote everything down correctly.
All right, I'm good.
All right, so our next example dealing with a continuous random variables x and y, and they have this joint PDF, x plus y, right? And we're going to be looking at the variance of x plus y. Okay, so so for this, right, we're just going to tell you that x and y are not independent. Okay, you can take it as read that we've tested it offline and I'm just telling you that they're not independent. So we need to be able to figure out, to calculate the variance of x plus y, we have to include the covariance part. So it's the variance of x plus the variance of y plus 2 times the covariance of x and y. So there's a lot of calculations involved in this one here, but we're just basically going to be following this. So I have to calculate out variance of x and then the variance of y and then my covariance. So for this, first off, to calculate these, I need the marginal PDFs. I need to calculate those first. Okay, so the marginal PDF, so my f of x is going to be, I'm going to go summing across all of my x values, x plus y, but for all of my, across all of the y, okay? So with respect to y, so this is going to be x, y plus 1/2 y squared, and this is going to be y equals 0 to y equals 1. Okay.
What did you multiply? So you have variance of x on variance of y, or variance of x plus variance y plus 2.
Covariance. Yeah, so two
Oh,
covariance.
that's covariance. Okay, sorry.
Yeah. That's my handwriting, right? My my pen kind of gives out a little bit sometimes too, so it's hard to, you know, make it exactly. I'm trying to work on my penmanship, but sometimes things conspire against me. All right.
Okay.
So this is x plus 1/2 gives us our marginal PDF for x. Okay. I need to do the same thing for y, so I'm going to scroll up a little bit here. I'm going to go fy, y, same process, right? We're going to go from 0 to 1, our joint PDF, and then going to sum it with respect to x. This is going to give us x squared over 2 plus y times x, and this is going to be x equals 0 to x equals 1. We're going to evaluate, and that's going to give us y plus 1/2. This is our fy of y, and this is our fx of x. Okay, our marginal PDFs, x and y. Okay. All right, let's move on to our expected values. Okay, so our expected value of x, which is our mean of x. Okay, so to calculate this, right, I have to take a look at 0 to 1 x. I'm going to look at x plus 1/2 dx. I'm using my marginal PDF to calculate my expected value of x. So now I'm going to go 0 to 1, x squared plus 1/2 x, and then this is all dx here, which is going to give me 1/3 x cubed plus 1/4 x squared, and we're going to evaluate that from 0 to 1. That's just the power rule. Okay, so our mu of x is going to equal to, in the end, 7/12. Okay. I'm going to do mu of x squared because I'm going to need that for my variance. Here. My expected value of x squared. Okay, so I'm going to go from 0 to 1, x squared, x plus 1/2 dx. Same thing that we were doing before, so 0 to 1. So this is x cubed plus 1/2 x squared dx, which is going to give us 1/4 x to the 4th plus 1/6 x cubed from 0 to 1. So my e of x squared is going to equal to 5/12. These are all pieces that I need in my calculation, right? Okay, it's a lot of work, but we can do it. Okay, so let's think about our variance of x. So e of x squared minus mu of x squared is equal to 5/12 minus 7/12 squared. Don't forget the squared part on this bit, right? That comes from here. And that's going to give us 11 over 144. Okay, this is our variance for x. Okay, I calculated it offline, and I got the variance for y. Okay, so I'm just going to give that to you. Was also equal to 11 over 144, right? You'd want to go through and do the whole thing, like for e of y squared and all that, and then calculate the variance of y. I calculated it offline just so we can move on. So we've got our variance of x, variance of y. Okay, everybody else said. I'm going to scroll up a little bit here. So I'm going to go e, oops, sorry, of x, y. Now, e of x, y is my double integral. So I have both variables I need to take into account. My joint PDF, and I think I did y first. Okay, so I need to distribute this to both terms here. So I can do power rule on things. This is going to be x squared y plus y squared x. dy dx. All I did was distribute this xy into both of these terms here, okay, to get.
So you use the joint when you're calculating.
I'm going to need it when I calculate the covariance of xy, because the covariance of xy is the expected value of xy, right, minus the expected value of x and the expected value of y.
Okay.
Okay, so let's see. All right, so let's go ahead and work our way through. So let's go ahead and do this integral here. So this is going to be 0 to 1. We're going to do the first integral. So we're integrating with respect to y to begin with. So this is going to look like x squared y squared over 2, right, plus x y cubed over 3. Notice how just the y's have changed. And this is y equals 0 to y equals 1. And now we're going to integrate with respect to x. Okay, so this is going to look like 0 to 1, 1/2 x squared plus 1/3 x dx. I'm going through all the calculus on it so you can see how we're thinking through and how we're working. I know it seems like I'm working through a lot of math here, but I think it might help you in the end just to see how these things work together. Okay, all the individual steps. Okay, so I worked this through, and then I'm going to get, let's write this down. So this is 1/6 x cubed plus 1/6 x squared, and I'm going to evaluate that from 0 to 1. And what I get out of that is 1/3. So that's my e of xy equals 1/3. I'm going to need that when I calculate my covariance. Okay. You guys, I'll give you guys a second to finish writing it, and I'm going to turn the page because I need more room. So we didn't show the calculations here, but we would also need to calculate e of y, okay, and then possibly e of y squared. I didn't have those calculations here, so I have them. I'm just going to give you the answers for those so you guys can test it out if you want to try things out. Is everybody done writing this part, or does anybody need more time writing it?
Just one.
Okay, no problem.
Okay, I'm good.
All set, great. All right, I'm going to turn the page so I have some blank page to work on. So remember, we got all these values here. Okay, so now I'm just going to tell you I calculated this offline. So my expected value of y is equal to 7/12 also. So we're going to you can test that offline if you want, calculate that yourself. So the covariance of x, y is equal to expected value of e of xy minus e of x times e of y. Okay, so I'm going to plug in the values that we just calculated. So this is 1/3 minus 7/12, and I'm telling you I calculated offline 7/12 for e of y. You can go ahead and try this out too if you want to check it out for yourself. So then this is equal to minus 144. Okay, so now this is our covariance, but now we're looking at the answer. The question that we were asked was the variance of x plus y, 11/144. I'm going to plug in the pieces that we have, plus 11/144 plus 2
Does that
times.
say a negative 144?
It's a negative. Yeah, it's a negative. And that's just going to mean that like one of these terms is going to dominate more than the other. Okay, it doesn't it doesn't mean, it's not like with variance things had to be positive. The covariance can be both positive and negative. Okay, so now we put it all together. This was equal to what I find. This is positive, equal to 20/144, which was approximately equal to 0.1388. Phew, it's a lot of work.
So covariance is allowed to be negative?
Yeah, covariance can be negative, but the variance itself has to be positive. Like the individual variances are going to be positive, but the covariance can be both positive or negative. And all it does is talk about like, you know, which because we're dealing with the covariance of two variables interacting with one another. And so all it is just kind of describing the nature of like which variable is varying in which direction. It isn't like a variance itself. When we think about variance on a a probability distribution. Variance is actually like a, when we get to actually the normal distribution, we'll talk about what it means calculus-wise, whereas our variance and standard deviation and our mean and all that. We'll describe those things, but variance itself is positive, but covariance can be both positive or negative.
Okay, sorry, it's just a lot to.
I know, right? There's a lot to take. There is. I know this chapter 3.9 and even 3.7, all these things, there's a lot to kind of assimilate and make sure that you understand. But this wraps up chapter 3.9. This example is our last example for chapter 3.9. Okay. You guys all done writing this part here?
I got it.
Okay, great. All right, so I'll scan in 3.9 lecture examples and I'll post them you know, later today so you guys can take a look at it. What I'd like to do, and we can talk about it if you guys want to vote. If you don't want to say anything in class, you can do it into the chat window if you want. But I'd like to start 4.2. If you think that 4.2, where it's only, we have like essentially a half hour, 35 minutes to cover 4.2. I want to get as far as we can because next week is a short week and I'm going to have less time to cover things because we only have 3 days of lecture instead of 4 like we would normally. So I'm okay with not including 4.2 in the quiz today and not having 4.2 homework be due, although it'll still be due next week. So I'll just re-include it in next week's assignment. And I encourage you over the weekend to start working on the homework for 4.2, even if it isn't due tonight. How do you guys feel about that? I'm asking if you want to not include 4.2 in the quiz today. I think I probably already know the answer, but I want to hear
Like
from
that
you.
plan. Yeah.
You like that plan?
Yeah, 3.9 is a ton of stuff, so like I don't want to have to like put even more on top of that.
Yeah, that's kind of my feeling too. I think for the quiz
Yeah.
today, for you guys to be able to assimilate all this stuff and then roll with it, and then on top of it, the Poisson distribution, which is really neat. So I kind of want to give it some justice, but it looks like I'm getting. I'm not seeing any votes for. Let's go ahead and include it in the quiz. All right.
So wait, so for homework 12, there's 4.2 and 4.3.
Homework 12.
Is that on purpose?
You know, so some of the, yeah, so you could ignore that. It just means that like the homeworks, some of the homeworks that I have are individual chapters and some of them are grouped together because when I teach this like in a like a fall or spring semester, we only meet twice a week, say for example, and then the homeworks get grouped differently.
Yeah.
So you can ignore it. Yeah, if it just says look at what when the assignment says like what chapters are included, then just go by that assignment. Okay, so what we thought this week was going to include 4.2, you would just read the 4.2 part of the assignment. Okay.
Yeah. So so is that also due today?
No, it's not. So what's going to be due tonight is 3.5,
Yep.
3.6,
Yep.
3.7,
Mhm.
and 3.9. There's a lot, right? I mean, I guess it's probably good that we're not including 4.2 on the homework and the quiz. And so although like 3.5 and 3.6, they're small and they kind of go into 3.9. You can kind of think about those 3 chapters as like one big concept, right? Because they deal with the mean and the variance, right? The expected values. And then 3.9 talks about 3.7, I'm sorry, talks about like, you know, how do we think about 2 variables together? So so yeah, I think that's probably enough for our quiz today. But what that means is you will probably want to do 4.2 homework over the weekend, you know, or at least start making a stab at it because next week we don't meet on Monday. There's no class on Monday. And then what's going to happen is we're going to roll right into, if we have any bit of 4.2 to finish up, we'll do it. And then we're going to roll right into other distribution types. And then once we introduce the normal distribution, which I think is 4.3, then we start using that as a basis for our statistical analysis. We start talking about statistics at that point. So keep it in mind. The class is fast because it's a summer class. Okay, so I think I've rambled enough. So 4.2 is not on the quiz and it's not due for homework tonight, but you should do some of those over the weekend because I won't also have office hours on Monday either. Okay, so no class, no office hours on Monday. So when you guys come on Tuesday, if you have any questions on Tuesday afternoon for office hours, we can talk about 4.2 in addition to whatever else new that we've been covering. Okay, great. So with that said, let's at least get through 4.2 as much as we can. Okay, so 4.2 is, let's start right out. So chapter 4.2. This is the Poisson distribution. And the Poisson distribution was named after a French mathematician whose name was Poisson, which if you guys speak French, Poisson means fish, so that was his name. But he kind of came up with this idea to describe a natural phenomena. So this is a probability. This is a discrete distribution, but it's a probability mass function. I'm going to be a stickler about mass so that even though we're describing this, often this can get described using a decreasing exponential, but it's really describing the underlying data themselves are discrete. Okay, so it's a probability mass function. And this models a lot of real world phenomena. Okay, I think it was they first came up with it when they were looking at like gamma, you can spell gamma particles. This was radiation. So how many particles in a minute, say for example, that were being given off by some kind of radioactive material can be modeled by a Poisson distribution. Other things like when we describe as some kind of like how many events happening within a given space, how many events happening within a given time. So one of the examples we're going to talk about is like the number of typos on a page, a printed page of a book. We can think about the number of fish that are caught in a given net, or like the number of cars that pass through like a traffic signal within a minute, say for example. Okay, so let's kind of codify that a little bit. So X, right, and there's some theory, some background stuff on this. I'm not going to just jump right in and give you the formula. I kind of want to show you like what some of this stuff is all about. So X is our discrete random variable. Okay, it's a discrete random variable, and it describes, or it somehow it codifies mathematically, say the number the number of times any given event occurs within some given time frame or some given space. So we think about this as the number of particles per minute, the number of something per minute, the number of fish per net, right? So it's something per something. So it's like a rate. You can think about it as a rate of things. Okay, so like we said, gamma particles. So that was how we would talk about that. So let's talk about things. We're going to build up to our Poisson distribution here. So we're going to first talk about a Poisson limit. Okay, so what is a Poisson limit? So we're going to use this to approximate hard to calculate binomial probabilities. Remember our binomial probabilities. Our binomial probabilities were like have a success or a failure. The event happens, yes or no. Does this drug in a drug trial, does it work? Yes or no? That kind of a thing. So, but they're hard to calculate, binomial probabilities. And why are they hard to calculate? It's because where we say that the values of n and p, which are like the crux of the binomial probabilities, right? The number of samples and the probability of that sample happening. We're going to say they're going to reflect, this is, I'm writing down the definition, and we're going to discuss like what does it mean. They reflect the conditions of the limit, but let me talk about what that means. So what happens is n gets really large, and then p at the same time gets really small. But at the same time, n times p is held constant. Okay, so if n times p is held constant, as n gets large, p gets small. Okay, so I've got this really large sample size. The probability of each event happening gets really, really, really small. But my expected value from this probability distribution remains the same. Okay, so this is fixed. And then often what happens is we don't know the exact value of n. We don't know the exact value of p, but we know what this constant is. Okay. So let's just talk about, this is our expected value for binomial distribution. Okay. So keep in mind, often when we have a lot of this, let me see if we can see that, we have a lot of this data, n and p individually, we don't know what they are, but we do know what their constant is. Okay, so what we're going to do is we're going to derive our Poisson distribution from the binomial. So the binomial kind of sits underneath our Poisson, right? But we don't know what n and p are individually. So let's just talk about how we get there. So we're going to derive, and this isn't like a mathematical derivation where I think our book maybe goes into more detail about how the derivation on this stuff, but I'm trying to give you, you know, where it's kind of coming from. But you should know that the Poisson comes from binomial. So if x is our binomial, random variable, okay, I'm gonna move this up here. So if x is our binomial random variable, then we say that the probability that x is equal to some value k, right? We can write it like this. It's going to equal to n choose k, p to the k, 1 minus p to the n minus k. This is our binomial probability distribution, right? And where k can equal 0, 1, 2, so on and so forth, all the way up to n, okay? So, but the problem is if n is going to infinity, right? And our p-value is going to 0, then I have to, I can't do, oh, but I need to write, but n times p is a constant. Okay, that means, right, n goes to infinity, p goes to 0, you know, proportionally speaking, so that their expected value, their mean, remains the same. It's a constant. I can't necessarily write it like this anymore. It's going to break down. So that's where we talk about the Poisson limit, because we need to think about this as a limit. So I'm going to say the limit as n goes to infinity, but I'm going to include also as p goes to 0, but n times p is a constant. Right, so all three of these things are happening at the same time within my limit. If that's the case, then the probability that x is equal to k is equal to the limit okay. Cell phone's ringing. All right, of this whole function here, n k, e to the k, 1 minus p, n minus k. So we've got this, our binomial distribution. We've got this limit that's happening. So I'm going to take the limit of my binomial as n goes to infinity, but p goes to 0, but their product remains constant. And what happens is it reduces down, this limit becomes our Poisson distribution.
Can you go back for?
Yeah, sure. Give me just a second. Okay, so it reduces down to, I'll let you guys finish writing that and then I'll flip the page. We're going to rewrite this so that we talk about this as a Poisson constant, okay, because we don't know what n and p are, we just know them as a constant term. So all I'm saying here is, right, we've got our binomial distribution here. I'm taking the limit as n goes to infinity, as p goes to 0, but n times p is a constant of my binomial. Probably should have written it over there. Because the Poisson comes from our binomial. Does this event happen? Yes or no? Let me know when you're all set.
And then this, the equation we're representing it by is on the back.
Yeah, right here. And then that's what that limit is equal to. This is our Poisson limit of our binomial distribution. But because we don't know what n and p are specifically, and n and p values are specifically, we're going to represent them by a constant. Okay, so let me just write down, I gotta write down. This is important. So Poisson distribution. So this is what we call the law of small numbers. Okay. So the first one is that we have no explicit binomial variable is present. We don't know. We don't know what n is. We don't know what p is. So I can't actually calculate the binomial distribution, right? So that's our problem here, one of the main problems. The other one is that the values for n and for p are not available. Okay. If they're not available, I can't use n times p, right? But I know what their constant is, what their product is, okay? So what I'm going to say is my x, which is our discrete random variable, so we're going to tell you when we do like homework problems or quiz problems and stuff that, you know, this event that's happening is represented by a Poisson distribution, so that you'll know, you know, how you can process it and how you can work it. In the real world, it's often you'll know because it's some number of things happening in like per space or per time. Okay, that's how you can, you know, typically safely model it as Poisson. So, but let's write down what our Poisson is. So we don't know what n and p are explicitly, but I know what their constant is. So I can say the probability that x is equal to k, I can also write like this, is e to the minus lambda times lambda to the k all over k factorial, where k can equal 0, 1, 2, so on and 3, so on and so forth. Okay, remember 0 factorial is equal to 1. Now lambda is equal to n times p, which is just a constant. That's our rate, you know, the rate of things happening typically, okay? This is our expected value, right, which is also our mean, right? That's another, expected value is another way to talk about our mean. Okay, so this is n times p, and then the variance of x is also equal to lambda, okay, in our Poisson. So this is, right, that's what we had written up before when I said np, you know, and then np to the k. But since we don't know what n and p are, but we know what the constant is, okay, I know what I'm going to be given lambda. I'm going to be able to figure out what lambda is from things, and then I'm going to be able to calculate what's the Poisson distribution of something, or the probability of something happening, given that I know that the underlying data is represented by Poisson. You guys are done writing that. Let's take out our lecture example page, and we'll start thinking about some examples for our Poisson. We'll start with example 1. All right. So example 1 here says, given the random variable x we're going to define as the number of typos on a printed page, say of a book or something that you're reading, and it has a mean of 3 typos per page. So look, so now I'm reading this. I've got a quantity of something per something else, per space, right? So I have 3 typos per page. Okay, so already that kind of makes me think it's some
Go
kind of
back for 1 sec.
you bet, it's a rate of something happening. Then we're going to ask ourselves, what's the probability? There, can you see that? What's the probability that at least one typo,
Thank you.
and what's the probability that at most one typo occurs? So 2 different questions. All right. So let's talk. We're going to use the probability mass function, okay, our Poisson distribution, because it's some kind of a rate of things that are happening. So I'm going to say probability that x is equal to k is equal to e to the minus lambda to the k all over k factorial. Okay, so that's my Poisson distribution right there. Okay, so at least one, right, is basically saying I could have 1, or I could have 2, I could have 3, I could have 4, I could have however many, you know, typos, however many, you know, letters are on the page. So at least kind of lends itself well to our complementary calculations, which is I'm going to say 1 minus no typos. Okay, that's going to be easier to calculate. Okay, so that means I'm going to go probability that x is greater than or equal to 1 is equal to 1 minus the probability that x is equal to 0. Okay, so x is our random variable, k are our possible values for that. Right, so this is, we're going to calculate 1 minus the probability that x is equal to, okay, which k is going to equal to 0. So I'm going to say 1 minus, this is a Poisson distribution, so my probability, I'm going to substitute in here. So this is going to be e to the minus 3. So my lambda is equal to 3, okay? Because our lambda, remember, is our mean, right? We were even told here in the problem has a mean of 3 typos per page. So lambda equals 3. This is going to be times 3 to the 0 all over 0 factorial, okay? Which is equal to 1 minus e to the minus 3, which is like roughly 0.9502. So the probability of finding at least one typo is like 95%. It's pretty high, given that there's like an average of 3 typos per page. Okay. All right. Okay, so part B says, what's the probability that some randomly selected page will have at most 1 typo? Okay, so at most 1 typo. So this is probability that x is less than or equal to 1 at most. At most 1 typo is less than or equal to 1, which is, I think, the summit, right? So that's basically probability that x is equal to 1 plus the probability that x is equal to 0. I could have no typos, or I could have 1 typo, at most 1. So that's fairly straightforward. So I'm going to go e to the minus 3 times 3 to the 1 all over 1 factorial for representing when x is equal to 1, plus this one here, e to the minus 3 times 3 to the 0 factorial. So I'm going to sum this up. This is 4e to the minus 3, which is like roughly 0.1992. Right, so this is like a 19.9% chance, like a 20% chance that I'm going to have at most 1, but a 95% chance that I'm going to have more than 1. Okay. At least 1. Okay. The Poisson distribution, there are different ways of setting up. We have like multiple ways of writing our Poisson distribution based on the problem that you're dealing with. This was our first form. They all follow the same general format, but you know, what lambda gets multiplied by, we'll talk about that as we go, because sometimes there may be a time involved in there. Okay. There are, by the way, we're starting to get into the realm now with defined probability distribution functions, where you can find, I think even in the back of our book, there are tables. Okay, so there are tables of probabilities that people spent a lot of time calculating out things, so that you can find cumulative, a lot of these are cumulative distributions. So if I wanted to do a cumulative distribution, remember, right, if I wanted to find out probability that x was equal to 4, say for example on a cumulative, I'm going to go probability that x is less than or equal to 4 minus the probability that x is less than or equal to 3, because 3 accumulates everything prior to that. It's going to take that away and just leave me with 4. Okay, so if you're reading these tables at the back of the book, which we're going to get into when we start talking about the normal distribution, we're going to learn about how we're going to read these tables. Remember, a lot of these are cumulative. Okay, so that was example 1. And let's keep talking about Poisson itself. So another way of thinking about the Poisson can be used to model events happening like within like time intervals, right? I can model the time interval between successive events using a Poisson distribution. Successive events that are happening, like we often think about like we use like meteor showers, you know, as can be modeled like the, you know, the meteors happening, the meteors coming to Earth happening, you know, so the time between each meteor that we see can be modeled with a Poisson distribution. But let's draw it out just so you can see what I'm talking about. So I've got this overall length of time. So this is my overall time window that I'm looking at. So I've got, you know, my first time window, my second time window, my third time window, so on and so forth. I've got my nth time window. That's where I stop kind of counting. now I've got events that are happening. So maybe I've got an event that happens in the second time window. I have an event that happens in the third time window. Okay, and I've got an event that happens here in this particular time window. So these here are events that are happening. Okay, and then this is the overall window, capital T is the overall window that we're looking at. We're sitting outside for like several hours watching the meteors come in. You know, every several minutes we're seeing something. So the time between each successive meteor that we see can be modeled by a Poisson distribution. So let's talk about this. So I'm going to start breaking this up. I've got n subintervals. I'm going to say that they're of equal length. Making them equal length is going to help me quantify the math and work it through, which means I've got the length on these is t divided by n. T is my overall time. I've got n subintervals. The length on each time window is t divided by n. Okay, so we're going to say that n is actually a large number too. Okay, because when I have a large amount of intervals that are happening, the math, especially binomial, things that are based on binomial data gets much nicer. All right, so let's kind of write down what we're thinking about here. So I've got the probability of more than at least 2 events occurring in the same interval is pretty close to 0, right? So if n is really large, and I've got this time window, if n is really large, right, that those time intervals are going to be really small. So the probability of having more than 2 events happening, like if I had, you know, 2 dots here instead of 1, it's going to be really, really small. So that's why we like to say that n is really large. The individual events occur independently. Right? The meteor showers, right? Okay, so, you know, we think about, you know, where the meteor showers are coming from, but each meteor crashing to Earth, we're going to assume is an individual event. Okay, but Poisson events are considered, the underlying data is considered to be independent. Third property, that the probability that an event occurs during a given subinterval is constant over the entire time, which goes from 0 to big T. Okay, which was, remember, that was like the prerequisite for our binomial data, right? That the probabilities can't change from trial to trial. Okay, so each independent event, okay, it's going to have the same probability of happening. Okay, each subinterval is like an independent trial, which is what I just said, trial in a binomial experiment. Okay, remember, our binomial experiment means the success is the event and the failure is no event. We often think success is equal to 1 and failure equals 0. So we sum up all of our successes. That gives us, you know, our number of experiments that are happening. Okay, so this is how we think about our binomial, yes or no, success or failure. Okay. So now with Poisson, we're talking about often with the time intervals between things, it becomes a rate, right? So if X is our discrete random variable, the underlying nature of the Poisson, because especially since it's based on binomial, is a discrete system, okay? But we have so many of these events that are happening that, you know, all of these like individual bars kind of fill in to look continuous, okay? But it's still, underlying data is actually discrete. So it's a discrete random variable for the total number of events, right, occurring during our time window, our big T, our overall length of time, okay? Which means that our lambda is the rate at which these things are happening. Events occur. Okay, I can have 2 events per minute. For example, okay. Which means that when we put it into our probability mass function for our Poisson distribution using this as a model, write out our Poisson. Using the Poisson distribution to describe the time in between events that is happening, we're going to talk about our probability mass function. It's going to look like this: P x of k is still a decreasing exponential times t over lambda t, all raised to the k, still divided by k factorial. So now lambda, remember lambda is a rate, right? So lambda is a rate, 2 events per minute. I need to know how many minutes we're looking, right? So that's why we're multiplying it by that in order to get our data to be just in terms of events that are happening, right? So this is here. Okay. And what I'll do is I'll stop here because we're going to roll into some examples for 4.2. We don't have that much more to cover for 4.2, but I'd like to, we'll just finish up 4.2 with examples on Tuesday next week. And we can work it through. So you should have enough to kind of think about if you wanted to try some of the homework problems for 4.2. If you want to wait to start them on Tuesday, that's fine. Just remember, we've got a lot that's going on next week. Okay. So I will have office hours today before our quiz gets opened up. So if you guys have any questions and you want to come by, feel free to. Okay. So to summarize, right, our quiz includes 3.5, 3.6, 3.7, and 3.9. Those are also the homeworks that are due tonight. Okay. All right, you guys.
Thank you.
Okay. See you later. Have a good weekend if I don't see you. And don't forget to take the quiz.
Thank
you.
you.
Bye.